Alright, we're on to section 1.7, analyzing graphs and functions, and piecewise defined functions, which they used to be called in my day, which was a long time ago, multi-ruled functions, but now they're called piecewise defined functions. And the first thing we want to mention that we want to look at for analyzing graphs is our graph symmetric to either a line or a point? Now, I have a couple of examples drawn out here, not very well. I tried to do my best there. So, you have a symmetry to a line, and in this case I tried to set this up so that my graph, this is the parent function of a quadratic function here. This is a parabola, vertex 0, 0. I tried to draw it so that, as you can see, the y-axis is a line of symmetry. It looks like it cuts it right in half, like a mirror image, one side flipped over to the other. A little bit more mathematical is that it's symmetric to a line if I can find any point. Let's call this point here P1. There is another point over here P2 always existing, such that if I draw the line segment between those 2 points, my line of symmetry will be a perpendicular bisector. And as you can see here, even though it's drawn kind of roughly, it looks like that could be a perpendicular bisector, that this could be a right angle right here, and that these could be the same size. Now, symmetry to a point is a little different, and I'm trying to draw this one out. This is supposed to be the cubic function, f of x equals x to the third power, and I have different scales here, as you can see on the x and y. Always important to set those scales. And what you have with symmetry to a point, and in this case the origin, it looks not like it's been flipped as much as it looks like it's been rotated 180 degrees. And more mathematically, if I have a point, let's say the point is right here, and I call that P sub 1, if you have symmetry, in this case to the origin, there has to exist another point, let's call it P sub 2, such that if I look at the line segment that connects those two, and that was drawn kind of poorly, there you go, that the point of symmetry, in this case the origin, would be the midpoint of that line segment every time. For every point P sub 1 there exists another P sub 2 such that that occurs. Now we can test for symmetry without having to look at a graph if we do the following things. Now we can look at symmetry first with respect to the y-axis. The graph of an equation is symmetric with respect to the y-axis if substituting in the opposite of x for x in the equation gets you back to the original equation, which is saying that I'm plugging in the opposite of x, but I'm going to get the same y. We have graph of an equation is symmetric with respect to the x-axis if substituting the opposite of y in for y in the equation yields back to the original equation. So the x stays the same, but the y is opposite. Well, that would tell me right away that if I have a graph that's symmetric to the y-axis, it's not a function, it's a relation, because it would fail the vertical line test. The graph of an equation is symmetric to the origin, like my picture up here is supposed to represent, if substituting the opposite of x in for x and the opposite of y in for y into the equation gives you back to the original equation. Well, in this case, you would plug in the opposite of x and the opposite of y in for x and y respectively. So we're going to do that with 3 examples here. I'm going to test for symmetry for all 3 themes here for these 3 examples. Determine whether the graph is symmetric with respect to the x-axis, the y-axis, or the origin. So we'll start with the x-axis here, which means that I'm plugging in the opposite of y in for y and x in for x. So that means I'm plugging in the opposite of y in for y and x in for x. Well, can this get back to the original? Well, even if I multiply both sides by -1, I do not get the original, so big no here. Not symmetric to the x-axis. And again, if you think of what this graph looks like, it looks like this one. So we should have symmetry to the y-axis, not to the x-axis. So let's check for the y-axis here. So for the y-axis, I plug in the opposite of x in for x and y in for y. So that would give me y into here. Y equals the opposite of x in for x there, quantity squared. Well, the opposite of x squared is the opposite of x times the opposite of x. Negative times negative. I'm going to get y equals x squared. I get back to the original, so this one is yes, as we expected. Now to see if it's symmetric to the origin, and we're pretty sure that this is not going to work, I would, for the origin here, I would plug in the opposite of x in for x and the opposite of y in for y back into the original here. the opposite of y in for y, and the opposite of x in for x. So again, we know what this is. This is x squared over here. This doesn't simplify. If I multiply both sides by -1, I don't get back to the original, so no, this one is not symmetric to the origin. Now, let's say you had a problem like that and the directions were similar to what I have, and you just graph it on your calculator and you say, oh, it's the y-axis. Well, that's not the kind of work that you would be responsible for showing. You would want to show that it's true, not that you can use technology to give at least an idea whether or not it's true. So you would plug these values in and show this kind of work. And so in this case, this is symmetric to the y-axis. Now in a little bit I'm going to show you, talk a little bit about the idea of an even and an odd function. And as it turns out, an even function is a function that is symmetric to the y-axis. This is an example of an even function. Alright, let's go over here to this example. I'll go for the x-axis again, so that means I'm plugging in x in for x and the opposite of y in for y. So that gives me the opposite of y, absolute value of it, because I'm plugging it into here, and I'm plugging in x in for x. Well, the absolute value of the opposite of y is equal to the absolute value of y, because the absolute value makes it non-negative, so whether y is positive or negative, the opposite of that, I'm going to get the same thing if I take the absolute value of just y itself. The absolute value of opposites are the same. And this stays the same, so yes, I get right back to where I started. This one is symmetric to the x-axis. This guy here, to see if it's symmetric to the y-axis, I'm going to plug in the opposite of x in for x and y in for y. Well, even if I multiply both sides by -1 to make this x look like that, everything else is going to change. This one I can see is not going to be getting back to the original. Now to see if it's symmetric to the origin, I plug in the opposite of x in for x, the opposite of y in for y. This simplifies to the absolute value of y, and I get right back to the same step that I was here when I was checking for the y-axis, so this one is no as well. And in this case, we have symmetry to the x-axis. Okay. My last example here, x squared over 4 plus y squared over 9 equals 1 is not a function. You can see if you try to solve for y here, you're going to get a plus or minus. And you may remember from your Algebra 2 days, that is actually the equation of what we call an ellipse that has center 0, 0. So in this case, I'm going to start for the x-axis. I'm going to plug in the opposite of y in for y. And we know that the opposite of y squared is the same as y squared. And look, I get right back to the original, so yes, this one does. This one is symmetric to the x-axis. And as I mentioned, it's not a function. Y-axis, I plug in the opposite of x in for x, and y in for y. And very similarly, I get right back to the original. So this is not only symmetric to the x-axis, this one is also symmetric to the y-axis. Okay, that means it's an even function. And now I'll check for the origin. And so I will plug in the opposite of x in for x, and the opposite of y in for y. And I have x squared over 4 plus y squared over 9 is equal to 1. And this is symmetric to the origin. You can't have symmetry to more than one thing here, and I have symmetry to the origin as well. Now, as it turns out, as a function that's symmetric to the y-axis, we refer to that as an even function. If it's symmetric to the origin, we refer to that as an odd function. So in this case, this one is symmetric to all three, and I'll write that out. Okay, and I think that, yep, that'll be enough for that.